In this video, we'll be talking about a time series concept called white noise. Now, white noise ends up being really important to time series because it answers the crucial question of when should I stop fitting my model. Of course, in other videos, we're looking at all different kinds of models and how you can fit them to your data, but at the end of the day, you're going to have some kind of residuals or the errors from your best model so far. And you're going to have the question about, could I have done better? Is there a pattern in the residuals that I should have captured and I need to add that to my model? Or am I truly done? We're going to see how white noise helps answer that question. So before we get into these pictures of whether or not something is white noise and why it's important, let's go ahead and just define the criteria you need for a time series to be white noise. So before that, I should just note that white noise is just a type of time series that meets these different criteria. Okay? So a time series is classified as white noise if it has mean equal to 0. That's one criteria. If the standard deviation or the volatility of the time series over time is constant, so if we have standard deviation is constant with time, and we'll see an example of how that's violated down here. And the last criteria is the correlation between lags is 0. So that means that there should be no correlation between the time series and a lagged version of the time series, whether that's lag 1 or 2 or whatever. There should be just no correlation at all. So I think the best way to understand white noise is actually to look at a couple of time series that violate the white noise criteria for various reasons, and that'll help you get an idea of when things are not white noise. Okay? So let's look at these two counter examples down here. Here's one. Let's see which one this violates. So the mean seems to be 0, which is the horizontal line here. So definitely not violating the first one. How about standard deviation is constant with time? Well, it seems like it's not moving up or down any more or less over time, so it seems like that's kind of constant over time. What about the correlation between lags is 0? Well, that here, this third one, is violated. And why is that true? Well, if you just kind of look at this graphically, you can say that if you're high, if your value is high at a certain time period, it's likely to be high at the next time period too, because this kind of looks like a sine wave, right? So if you're at this timestamp here, then you have a pretty good idea that you're also going to be around that value at the next timestamp or the previous timestamp, which means that the correlation between lags is definitely not 0 in this case. So this is not white noise for that reason. Now let's look at this one. The mean is again 0. It's clustered around this line 0 here. The correlation between lags, is that equal to 0? It may or may not be. We have these weird spikes here, so it's hard to tell that one, but it definitely violates the second one, which is the standard deviation is constant over time. For example, we see that there's periods of low volatility here and here, for example, where it's not moving much, and then we have periods of really high volatility here, here, and here, for example, where it's moving up and down a lot. So the standard deviation here is not constant with time, and therefore this is also not white noise. Now, to kind of match up this definition to these examples and why they make sense, in both these cases, we could have done more to capture the dynamics of these time series. In the first one, we should have captured this sine wave-like movement somewhere, and in the second one, we should have captured this increased volatility and accounted for it before getting the residuals. So we see that these criteria that make something not white noise or is white noise help us understand when we could have done more to the time series in order to capture the dynamics better. So only if the three criteria are met here, and it's truly white noise, then we cannot have done any better, because one of the biggest properties of white noise is that it is not predictable. So that says not predictable. So if you have a time series that's white noise, just don't even bother trying to predict it because it's not predictable by definition. So why is it important? Whenever we do a time series analysis on some time series y sub t, we always assume it's the combination of a signal, which is stuff we can predict and stuff we can make a model for, and noise, which is white noise, aka something that's totally unpredictable. We could not have predicted it in any way whatsoever. So it's important because if you truly capture a time series perfectly, that is, if you figure out all the components that make up the signal, whether that's autoregressive, moving average, more complicated stuff, then that means that the resulting residuals, remember, noise would be the time series minus the signal, would be white noise and therefore unpredictable. So if you can prove that your residuals are white noise or really, really close to white noise, then you can say that this is a great model that fits this data. Okay, so that's why white noise is important. Of course, the last concept in this video is how do we test if something is white noise? Of course, we looked at these two and kind of went through the criteria, but are there a different battery of tests we can run to see if something is or is not white noise? Now you can get pretty complicated stats-wise with this, and you can run some pretty official sounding tests, and we might make some future videos. But in the interest of keeping stuff kind of accessible to everybody, I wanted to kind of just go through 3 tests you can run that helps you begin to understand if something is or is not white noise. The first one is, of course, visual tests, which is what we did up here. We looked at them and said that something seems fishy about them, therefore it's not white noise. The second one is we can run global versus local checks. What that means is, let's say you have a time series, you're trying to figure out if it is or is not white noise. You can calculate the mean and variance of the entire time series, and then you can also that would be global, and then you can also calculate the mean and variance of slices of that time series. So maybe you do a rolling window. Let me switch colors here. Let's say you do a rolling window of this time series of 7-day chunks. So you do this 7 days, and you do this 7 days, and you do this 7 days, and you just roll that window. And for each window, you calculate, again, the mean and the standard deviation. And those means and standard deviations, the local ones, should match up to each other and also to the global one if this is truly white noise. Because, of course, the mean should be 0 at all times, and the standard deviation should be constant at all times. That's a second set of tests you can run. And the third one is to capture this last criteria, which is the correlation between lags should be 0. Of course, we can use our old friend, the parallelogram, which, just to refresh, looks something like this. Of course, the x-axis is which lag you're at, and then the y-axis is the correlation between the time series and itself lagged at 1 or 2 or 3. And of course, we throw on these error bands. Anything within the error bands is not statistically different from 0. So if we did a parallelogram of a truly white noise, we would expect them all to be really close to 0, not outside the bands. Of course, in practice, even if something is white noise, you might just by accident get some of them going a little bit above the bands. But the point is, we should never see something like that, where it's very, very, very big evidence that the time series is correlated with itself as lag 1, for example. Okay, so here's 3 tests you can run to check if something is or is not white noise. So you can have a set of data. You can try your best to fit a model to it. You'll have some residuals. Run it through these 3 tests. If it passes all of them, then you have more confidence that this residuals is white noise and that you did a good job of modeling the time series using your signal. Okay, so that's a brief introduction to white noise. In the future, I think we'll do some more robust tests to see if something is white noise, but these should get you going for now. Okay, so until next time.